For this question, we want to answer the three parts using the function and its derivative. Use calculus techniques to solve the problem and show your work on the scratch paper to earn full points. Since the derivative is given, you do not need to calculate it. So we're given a function f, which is x times the square root of 2x plus 1. We're also given the derivative of f, which is f prime of x equals 3x plus 1 over the square root of 2x plus 1. We want to find the critical numbers of f, find the intervals of increasing and decreasing for f, and identify the relative extrema for f. We're going to write our answer as an ordered pair and also identify which type of relative extrema we have, whether it's a minimum or a maximum. So starting with finding the critical numbers of f. The critical numbers of f are where the derivative is equal to 0 or the derivative is undefined. These critical numbers also need to be in the domain of the original function. So we have the derivative given to us to be f prime of x equals 3x plus 1 over square root of 2x plus 1. We can find where that derivative is equal to 0 by setting the numerator equal to 0. And we can find when that derivative is undefined by setting the denominator equal to 0. We'll set 3x plus 1 equal to 0 to get our critical numbers. That's 3x equals negative 1 when we subtract 1 from both sides. Divide by 3 and we have x equals negative 1/3. We'll also set that denominator equal to 0 and solve, subtracting 1 on both sides. That's 2x equals negative 1. Divide by 2 and we have x equals negative 1/2. So these are the critical numbers of f. In the next part, we want to find the intervals of increasing and decreasing for the graph of f. To do that, we build a chart using the real number line and the critical numbers we just found. And on that number line, we'll mark negative 1/3 and negative 1/2. Negative 1/2 is smaller than negative 1/3. So we put them in order. And then one other thing of interest for this example is the domain of this function f. Because we have a square root, we have a restricted domain, versus if f were a polynomial function, your domain would be for all real numbers. So I want to consider this restriction on the domain. We know that for square roots, if you square root a positive value, you're going to get a real number. If you square root of 0, you get 0. However, if you square root a negative, you get imaginary numbers or complex numbers. And we only want to consider real numbers. So to find the domain of a radical, you're going to take what's underneath the radical and set that greater than or equal to 0, which is restricting you to only being positive or 0 underneath your radical. So if I subtract 1 on both sides, divide by 2 on both sides, we get the domain for this function to be x is greater than or equal to negative 1/2. So that means any value less than or equal to negative 1/2 is excluded from the domain. So this portion of the number line is not considered in this problem because it's not a part of the domain of the original function. So when we're looking for intervals of increasing and decreasing, we only need to test the other two intervals. So we're going to pick test points in each one of these intervals, and negative 1/2 is negative 0.5, and negative 1/3 is negative 0.33. So let's pick negative 0.4 as our test point in that interval, and then we can pick 0 as our test point in the other interval. We're going to substitute these test points into the first derivative, because the first derivative is the slope of the tangent line, and when the slope of the tangent line is positive, we know we have an increasing function, and when the slope of the tangent line is negative, we have a decreasing function. So we're going to take those test points of negative 0.4 as well as 0 and substitute them into the derivative. We have 3 times negative 0.4 plus 1 over the square root of 2 times negative 0.4 plus 1. So we want to think about whether that's positive or negative. So we have 3 times negative 0.4 plus 1. And that gives me negative 0.2 in the numerator. And in the denominator, we have 2 times negative 0.4, which is negative 0.8 plus 1. So that's going to give me a positive in the denominator. So we have a negative divided by a positive, which is a negative. So on this interval, let's use purple to represent it. On this interval, our first derivative is negative, which indicates the function is decreasing on that interval. And then let's test the other point. Test the other interval. We have 3 times 0 plus 1 over square root of 2 times 0 plus 1. That's a positive over a positive, which is a positive. So on this interval, our first derivative is positive, which indicates the function is increasing on that interval. So we would state that this function is increasing on the interval from negative 1/3 to infinity, and this function is decreasing on the interval from negative 1/2 to negative 1/3. And then for our final part, we want to identify any relative extrema. Relative extrema is when we have a change from increasing to decreasing or decreasing to increasing, which we have in this example. Over this point of negative 1/3, you can see that we have a change from decreasing to increasing. So if we think about that, a change from decreasing to then increasing will create a relative minimum, and that relative minimum occurs at x equals negative 1/3. So we know that this function has a relative min at negative 1/3, but we want to make sure we write that as an ordered pair, as the directions state here. So we're going to substitute that negative 1/3 into the function, the original function f. So f of negative 1/3 is negative 1/3 times the square root of 2 times negative 1/3 plus 1. Negative 1/3 times the square root of negative 2/3 plus 1. And that's negative 1/3 square root of 1/3. And we have, let's see how we can simplify that. That's negative 1/3 Square root of 1 is 1. You can leave that square root over the 3 in the denominator, so we have negative 1 over 3 square root of 3. We could rationalize this as well by multiplying by square root of 3 over square root of 3. So that's negative square root of 3 over 3 times 3, and that's negative square root of 3 over 9. So the ordered pair negative 1/3 negative square root of 3 over 9 is the relative minimum for our function f. We're going to use calculus techniques to solve the problem. Show your work on the scratch paper to earn full points. All the edges of a cube are expanding at a rate of 3 inches per second. How fast is the volume changing when each edge is 5 inches? Use V equals S cubed, the volume equals the sides, one side cube, for the volume of a cube. Write your answer in the blank and the units in the other blank. So we want to keep track of the units for this problem. So let's start with the given information. We're given that the edge of a cube is expanding at a rate of 3 inches per second. So when you have a cube, you have a figure that looks like this. The cube is three-dimensional, and it has, because it is a cube, all the sides are the same. So we have dimensions of S, S, and S. For the length, width, and height, it's all the same. And so the edge is referring to the side. This is also indicating a rate of change. So it's not a fixed value of the side, it is the rate that the side is changing. So we're going to represent that as ds dt. We have 3 inches per second. And as we continue, it says, how fast is the volume changing? How fast is the volume changing is referring to the rate that the volume is changing, and we'll write the rate the volume is changing as dv dt. And that is our unknown in this problem that we're trying to find. We're interested in the moment when each edge is 5 inches. The edge is the side. So we're interested in that particular moment when the cube is expanding to the point where we get to 5 inches. So we have this formula which represents the volume of the cube, V equals S cubed. And in order to solve this equation, we need to introduce these rates of change into this formula. The formula that we're looking at here is a geometry formula for a fixed size figure, but we have a figure that's changing. So we're going to introduce the rates of change into this formula. So to do that, we calculate the derivative with respect to time on both sides of the equation. So that's the derivative with respect to time on volume and the derivative with respect to time on the sides cubed. So the derivative with respect to time of volume is dv dt, the rate of change of the volume, and then the derivative with respect to time on s cubed. We need to follow the chain rule to calculate this derivative. So we'll calculate the derivative of the outside function first. The outside function is the cube, and that's a power. So we're following the power rule. So we bring that power down and take 1 away from the power, but we have to chain by multiplying by the derivative of the inside, the derivative of s. ds dt. So now we have introduced the rates of change into this formula. And I'm going to take a look at the formula I have as well as the given information and make sure I have everything I need to solve this question. So looking at this given information, I have ds dt, which is 3. I have s, which is 5. And my unknown is dv dt, the rate of change of the volume. And that takes care of all of the variables within this question. So I have enough information to solve for the rate of change of volume. I'm going to substitute into this formula. And as I substitute, I'm going to keep track of the units. So in for S, we have 5 inches squared. And in for ds dt, the rate of change of the sides or the edges is 3 inches per second. So following order of operations, I'll apply the exponent first. 5 squared is 25. I also square the units, so I have inches squared. And we'll multiply those numbers together. 3 times 25 times 3 is 225. And if I multiply the units together, inches squared times inches is inches cubed per second. And so we have that dV dt, the rate that the volume is changing, is 225 inches cubed per second. And as we look at these units, those units make sense because volume is a three-dimensional figure and our units are reflecting that three-dimensional figure in 3 dimensions, inches cubed. Thank you for checking out my videos. Have a great day.